Now we are in Utah. Okay, now we are in. Okay, thank you very much. We are already live, so please don't say anything. So we are already in Zoom, I guess, and through YouTube. Okay, so we welcome today Hareesh. I'll try to Thuruthipilly.
Yep.
Kind of. He's now in the University of Valladolid, not very far from here, a few hours by train. He did his PhD in the here, National Center for Nuclear Research in Poland, in Warsaw. And after that, he was for 6 months a postdoc there, and then he moved 3 months ago to the University of Valladolid. So he's going to talk today about tracing the faint universe, laws of brightness, galaxies in wide field survey. So we expect something like half an hour talk. So let's thank Hareesh again for coming here, for visiting us. Since you are not very far, hopefully that won't be the last of your talks here. We'll have more opportunities to enjoy your science. So thank you very much. Please go ahead.
Yeah. So hi everyone. Thank you for the opportunity to present my work. So today I'll be talking about identifying low surface brightness galaxies from wide field surface or even deep field surface. So, just to give a brief introduction about what is a low surface brightness galaxy. Currently, in the literature, there is no strict definition for what is a low surface brightness galaxy. But in generally, these galaxies are defined as galaxies that are fainter than the night sky. And but if you look into the literature, you can see depending on the which wavelength or which filter you are going to observe, you can find varying definitions for what is a low surface brightness galaxy. But the general idea is that these galaxies are very faint, very hard to observe, and they are also very crucial for our understanding of galaxy formation and evolution. Within loss of brightness galaxies, there is a class of galaxies which needs special mention. These galaxies are called ultra-diffuse galaxies. So these galaxies have typical sizes that is comparable to that of normal Milky Way-like galaxies, but only have a stellar mass of around 1/1000th of Milky Way-like galaxies. So these galaxies are very extended, but do not have much star-like star formation or stars inside these galaxies. So the general picture about UDGs is that these galaxies are an extended tail of the dwarf galaxy population, but there are also other claims about these galaxies are like failed Milky Way-like galaxies, but it does probably not too many people are following that. So the general consensus is that these galaxies are an extended tail of the dwarf galaxy population. Now the important question: so these galaxies are very faint, very low surface brightness. So why do we need to care about these galaxies, or why do we need to study about these galaxies? So currently, all the cosmological simulations based on the simple lambda CDM model predicts that the majority of the galaxy population resides in the low surface brightness regime, and also more than 50% of the galaxies are faint and also not represented in a current galaxy catalogs. So this has two important consequences. So if you understand all the galaxies that are bright, and if you create a theory about galaxy evolution and formation just based on the brightest galaxies, then you are kind of biased because you do not including the faint galaxies. And also, since majority of the galaxies that are in the faint regime, you are also having an incomplete picture. So without the LSBs, you will have an incomplete picture and also a biased picture of galaxy formation and evolution. And also not just only for the galaxy formation and evolution, it also affects the cosmology. So if you look at the predictions from the lambda's 3D model, it actually agrees with the large scale structures and also have very good agreement with the observations in the larger scales. But if you go to the smaller scales, and especially in the dwarf galaxy regime, where is the stellar, so dwarf galaxy regime is where the stellar mass is less than 10 raised to 9 solar mass. So if you go into that regime, you have like lot of small scale tensions or cosmological tensions, which are collectively known as the small scale crisis in cosmology. So the one of the potential reasons for this small scale tensions is our lack of understanding in the dwarf galaxy regime or in the low surface brightness regime. And also these galaxies are mostly dominated by dark matter. So we can also probe the nature of dark matter and answer a lot of important questions such as what is the exact nature of dark matter, stuff like that. So in short, these galaxies are very important not only for galaxy formation evolution and also for cosmological studies as well. So if we know that they are important, then the question is why don't we just go and find them and study them? So the answer is that it's not very simple. So we have mainly three problems. First one is that we need very deep surveys to detect these galaxies. For instance, in STSs, if you look at low surface brightness galaxies, you cannot find many low surface brightness galaxies because STSs was not very deep. But with the third generation surveys such as HSCSSP or Hypersupricam Strategy Survey Program, Dark Energy Survey, Kilodegree Survey, with these third generation surveys, we are kind of uncovering a small population of the or small fraction of the total loss of brightness regime. But and also with Euclid and LSST, we are going to cover identify a lot of LSBs as well. So the need of deep surveys, the problem with deep surveys is kind of solved in the current era. And the second problem is the problem with the sky background subtraction or sky background elimination. So as these galaxies are defined as very faint and also their surface brightness is comparable to that of night sky, if you do not do a proper sky background subtraction, probably you are going to destroy the LSB features. So you need to have very careful pipeline for doing this, and it's not very easy as it sounds. But for like the current generations, and usually the other problem is that usually like the wide field surveys such as Euclid, LSST kits, these surveys are designed for not for LSP science. These are designed for mostly cosmological sciences. So they don't. So the current sky background subtraction we have actually is not very LSP friendly. So if you look at the images, you can see that a lot of the LSB features are kind of getting destroyed. But currently, people are working to do a way around that. So if you have a deep survey and if you have a very good sky background subtraction pipeline, then the next problem is the presence of contaminants. So within the LSB regime, you can have a lot of contaminants. These contaminants can be either physical origin and also of instrumental origin. So when I say instrumental origin, there is nothing there. It's just that your instrument is not doing a very good work. So it might be coming from the reflections from a bright galaxy, or maybe sometimes it can be also coming from a tidal ejecta from a nearby galaxy. Sometimes tidal tails can be interpreted as or misinterpreted as loss of brightness galaxies. So it's a wide variety of contaminants in the LSB regime. To give a brief overview, so in 2021 in Dark Energy Survey, Tanaulis did a LSB search for and found that around 23,000 sources are there in the dark energy survey, and this is the distribution of the surface brightness and also the number of sources in surface brightness field. You can see that as you go towards the very faint surface brightness regime, the total number of sources detected is actually very huge, whereas the actual number of LSPs is very, very small. So if you go to 26.5 or 27, then you will have like a ratio of 1:10,000 for the LSP to contaminant ratio. And for his search for LSPs, what he did was that he used a pre-selection based on color cuts and also like surface brightness and size cuts. And then he did a support vector. He used a support vector machine to identify potential sources, and then he did a visual inspection for all the sources that support vector machine said is an LSP. And he found out, so he had to visual inspect around 40,000 sources to identify these around 23,000 sources. So which means that around 50% of the sources he visual inspected was not actually LSPs, it was actually contaminants. So which means that if you go to Euclid and LSST, if you scale that up to LSST and Euclid, they are going to identify around 100,000 or more than that LSPs. So you have to visual inspect around more than 200,000 or 300,000 sources to identify the actual number of LSPs, which is kind of impossible, and you have to be a superhuman to do all this visual inspection by yourself. So in this scenario, what we do is we go for better models, for deep learning models. So since our task is just a simple visual classification problem, just for looking at a galaxy, usually if we know the surface brightness parameters, you can actually easily distinguish between an LSP and a contaminant. So it's just that you cannot scale it to more than 100,000 or 200,000 of these galaxies. But with deep learning models, you can actually do that because it's a simple task of just visual inspection. So one thing is that we do not know the redshift of these galaxies, so we do have to have the follow-up studies. But just from the having a potential candidate, this can be done. So if you look into the current trend in computer vision, so the previous best performing models were termed as CNNs or convolution neural networks. So they were performing very well. This is not just in astronomy. This is the picture in computer vision in general. So the best performing models were aimed as convolution neural networks, and then after 2016 and until the period of 2020, we had advanced CNN models where they have much more complex networks and much more complex patterns in the architecture. But after 2020, the current best performing models are based on an idea called transformers. So probably you might have heard about a lot of transformers from popular literature, also from your physics textbook. So I could have chosen the physics textbook, the electrical transformer, but I opt to go with Optimus Prime for now. Sorry about that. So, and another transformer that you might have heard or might have used, but maybe not familiar with it, is the ChatGPT. So ChatGPT is actually a transformer-based model. So we are also using actually the transformer-based models, but not ChatGPT, but something similar to the core idea of ChatGPT. So any transformer model is based on the idea of self-attention or attention. So the basic idea of any deep learning model is how our brain works or how our nervous system works. So transformers are also based on this how our human eyes see an object. So if you look at an object, you don't exactly compress all of the information. You just only look at the relevant pictures of the relevant facts of the image. And also when I'm speaking or when you are hearing something, you probably do not listen to, probably you will listen to all the words, but you are not going to understand all the words. You only look at the important parts that is relevant to you. For instance, if I'm saying something and if it's boring, probably you are not going to listen to any of it. But if it's interesting to you, then you will try to listen to some part of it. but not all part of it. You are not going to remember all part of the speech that I am giving today or maybe in the future. But for sure, if it's interesting for you, you will understand some part of the text and try to understand what is going on. So, and that is just giving attention to the relevant features. So the transformer models also do the same. So if I give an image to a transformer model, it tries to understand what is the relevant features of an image and then tries to predict or try to do a classification task or try to do a regression task based on the relevant features of an image. So this is the basic idea of an attention mechanism, and any model that uses an attention mechanism can be considered as a transformer model. So here, just as an example, I have shown an image of a dog with a code. So if I just only showed this image, it's very, and ask you to give a context about this, it's very hard to distinguish. But if I'm asking you to classify what this source is. So unless I don't have this part of the image, it's very hard to understand what is going on. But if I only show the nose and also the ears, then probably you can guess it's a dog. But if I change the question to what is the background or where this image has been taken, then just showing only the images of the dog will not help you. You will also have to know the features such as the jacket or the coat or stuff like that. So depending on the question that you are framed or depending on the task, the features will have relative importance. So this is the idea of attention. So they try to assign different weights or different weightage to the features of the image or features to the input, and then try to do a task that you have designed. So this is the basic simple idea of attention mechanism, and here I am using two different kinds of attention models or transformer models. One is called a detection transformer and other is called vision transformer. So this has been introduced by so the detection transformer has been introduced by Facebook, and this one has been introduced by Google in like 3 years ago. And I'm not exactly using their architecture. I'm just like copy pasting some of the features or the architecture and then try to build our own architecture, because these models are very complex and we do not need that many complex models for our simple tasks. So now we have a good model for detecting LSP. So I decided to use the already existing data sets of Tanoglyphs from the dark energy survey, and also here, since he has inspected around 40,000 sources and only found 20,000 sources as LSPs. The rest 20,000 were contaminants. So I used the total 40,000 sources that he made publicly available, thanks to him. So we were able to design a transformer model, two types of transformer models, and this is the performance of the transformer models. And Tanoglyphs also has created a convolution neural network model to see how well the deep learning model will perform. So this is the classification accuracy which is achieved by the convolution neural network model, and this is the classification accuracy achieved by transformer models. So the increase is not very high; it's like almost 2%. But if you scale that up to LSST and Euclid, these are the numbers that you are going to get. So when you look at the accuracy of these percentages, even though the increase is very small, when you scale it up, it actually gives a lot of information and also makes our life very easy. So once we have the deep learning model, we decided to look for new sources that LSBs or new LSBs that the Tanoglyphs search might have missed. So we took all the sources in the dark energy survey and then applied our machine learning models. Not all the sources in the dark energy survey, all the sources that satisfy some of the pre-selection criteria set by Tanoglyphs, just to be consistent with his work. So we used the same initial sample and then did our machine learning search. Then we ended up with 4,000 new sources that the previous search have missed, which is around 70% of the total sample, which means that the previous method had a lot of bias. And also when we were doing this visual inspection, the total number of contamination was around 6% compared to the 50% that he had. So we improve the statistics, we improve the total sample size by 17% and also reduce the contamination rate from 50% to 6%. And these are some of the examples of LSPs that we have found. So usually the problem with deep learning models is that if you have a deep learning model, it will work very well on the training data or and also on the same data sample. If it will work on very good on the test data if it's coming from the same survey. But if you go to a different survey, if you train a model on one survey and if you use that model on a different survey, usually the performance drops. You cannot get very good accuracy or good very recovery rate. But we wanted to see that since we have a model that is well trained on dark energy survey, we wanted to see if it can be applied to detect some low surface brightness galaxies from other surveys as well. So we decided to go with the kilodegree survey and also the data from the HSC CAM. So this is not coming from the HSC SSP survey. This is private data of 8 clusters thanks to one of our collaborators, Jim Koda. So we used this data and this data. So the idea was that if we can go from dust to HSC and KIPS, then with the same methodology, we can try to go to LSST. So we don't have to visual inspect and label a lot of sources to train the models when the LSST or the Euclid data comes. That was the idea. So for that, we use the data from the ABEL 194 cluster. So ABEL 194 cluster is already been observed in dark energy survey. So we already know how many LSBs are there. And for this deep data of ABEL 194 cluster, we had actually much deeper data than the dark energy survey. So this is around two magnitudes deeper than the dark energy survey data, and this is also equivalent to the 10-year coordinate depth of the LSST. So if our model works well on this data, then we can safely say that our model will be fine on the LSST data as well. That was the idea. And the ABEL 194 is around 1 square degree has a radius of around 1 square degree. So it's not a very large data set. So our idea, and also the problem with going from one survey to another is that usually if you go from one survey to another, the problems are like there is different 0 points, there is different PSFs, and there is also different instrumental artifacts. So in order to solve that, we tried to, instead of using the raw images, we converted all the images for both dark energy survey and for HSC to its surface brightness units, so that the 0 points of the surveys will match in the final image. So this is the image from dark energy survey, and this is the raw image from HSC. You can see that the pixels values are not exactly same in both images, but once we converted it to the surface brightness units, you can see that the pixels get matched. So the idea is that over an average area, that the average sum of the pixels seen by the model in both regions will be same. So it will not matter if it's coming from a different survey. So we try to match the 0 points by converting it to the surface brightness units. And also to match the PSS and also the pixel scale, we try to rescale the images into a smaller resolution, to a common smaller resolution. So it's kind of like standardizing the data, but it's not the perfect standardization, but we wanted to see if it would work. So fortunately it worked. So we also looked at all the sources in the data, and we found out that, and once we have the LSB sample, we tried to feed that sample into the machine learning model, and we found out that the model was able to identify around 93% of the sample. And majority of the sources that we have missed had two reasons. One is that they were not very well represented in the training data set. Even though there was only small representation, we were able to still recover some of the very faint sources, but not all the faint sources. And also the other reason was that these sources, some of the sources that were missed had very bright sources nearby, which was causing the model to understand what is going on. So we had these two problems. But one other thing we noticed is that the total parent population of the LSBs is actually kind of similar to the training data set. But if you go to a different cluster, such as the Coma, where the surface brightness distribution is, the galaxies are much more farther because it's at a different redshift. So these galaxies are more fainter. So without fine tuning or without retraining, we cannot exactly recover all the population. So with just a simple renormalization of the surface brightness, we were only able to reach up to 80% recall. It's not very well, but we are currently working on that. But at least we will have a working sample of LSPs if you want to have like a very quick LSP sample. So all these searches were actually done on a very smaller area, less than 3 or 4 square degrees. So we wanted to see how well the model will work on a larger field of area. So we decided to go from dark energy survey to the kilodegree survey. So we use a similar surface brightness normalization and similar pixel scale matching by converting to smaller pixel scales. So we did the similar pre-selections and tried to identify all the sources in the kilodegree survey. And this is the total number of sources we have. We identified around 22,000 LSPs. And also, since KIDS field is also well studied from other surveys, we knew some of the sources which are LSPs that are in the same field. So within the non-LSPs, we were able to recover more than 95% of the sources. And also, when it comes to contamination, when we were looking for visual inspection, we also did some cuts on the specific profile fitting. and with that profile fit, cuts on the Celsius profile fitting, the contamination rate was reduced to 2%. So the kids field is actually well covered by a lot of spectroscopic surveys, and usually these galaxies, since LSBs and UDGs are very faint, getting the spectroscopic redshift for these galaxies is a very hard task. So we decided, and without the spectroscopic redshift, we cannot say these galaxies are actually intrinsically faint, or they are just faint because they are very far away from us because of the cosmological thing. So since we cannot get the spectroscopic redshift for all these sources, we just decided to cross-match all the sources with non-spectroscopic and H1 surveys to get, and also the cluster catalogs, so that any source that are within the virial radius of the cluster will be considered as a cluster source, and we can associate the redshift of the cluster to that source. So with these kind of cross matches, we had redshift from the 22,000 sources. We had redshift for around 4,960 LSPs, or around 5,000 LSPs, and among these 5,000, around 700 or 800 were considered classified as UDGs as well. And these are some of the examples of LSPs and UDGs that we have found. So the first row is the LSPs that is without redshift, and the second row is the LSPs that have spectroscopic crossmatch, and third row is the UDGs. So since we have the redshift, we also try to see how the star formation means, how these LSPs will look like in the star formation main sequence. So star formation main sequence just means that if you have a galaxy, then usually for star forming galaxies, the star formation rate and the stellar mass of the galaxy will be correlated. So we just want to, and this is known for normal galaxies, and usually extending to the dwarf regime, it's not very straightforward because we don't have a lot of samples for the dwarf galaxy regime. And since most of our galaxies were in the dwarf galaxy regime, not towards very faint end or towards low mass end, we just decided to see how it will look like. And this is the main sequence we found. And this blue line and also these lines are from the literature. So in general, we have a very good agreement with the literature values, and we also see that majority of the galaxies are formed actually on the star forming main sequence, and some sources are a bit far away, and these galaxies are considered as quenched. So when we say quenching, it just means that even though this galaxy have this much stellar mass and expected to form this much stars, it's not forming that many stars because of there is lack of gas. So or in short, the star formation is suppressed. So usually these galaxies, usually this can be an environmental effect for LSPs and UDGs because these galaxies are very faint. Their potential is not very great. So if you are towards a very dense regime, most of its star forming material will be stripped away from these galaxies. So we try to see if for the cluster LSPs and cluster UDGs, how the optical color will change as a function of the cluster centric distance. And we see that towards the cluster center, we have more redder color, and towards outer skirts, we have more bluer color, which means that towards the outer skirts, the galaxies are becoming more redder or becoming more quenched. But the error bars are actually larger. So we decided to see how this will look like in the main sequence. And here, these are the field LSPs and field UDGs, and they follow the star forming sequence very good. But these are the LSPs and UDGs in the cluster, and here you can see that for UDGs, the LSBs and UDGs, they are actually deviating from the main sequence, which means that they are kind of they are harassed by the environment, and their star formation is being suppressed. And also, towards very high clusters, unfortunately, we don't have many data points. So, So to conclude, what we have presented or what we have devised is that a cross-survey LSB identification pipeline. And the good thing with this is that it's not only usable for LSB identification. If you are working on strong lensing, or if you are working on galaxy mergers or any kind of galaxy classification task, you can actually do the similar methodology and try to adapt it, and probably should be working. We haven't tried for other classification tasks, but probably it should work. And with this, we also identified around 20,000 new LSPs from the KiloDB survey, and we also have the morphologies for these galaxies from the classification. And for these galaxies, we have around for 5,000 sources, we have the redshift, and the sources with the redshift also follow the main sequence of dwarf galaxies. So that's it. Thanks.
just was wondering to know about the technical part of the models. To confirm it was a supervised machine learning model. So, which were the labels, the information that you gave it?
Okay, so this was a supervised machine learning approach. So for the creating the data set, so we already know what were the LSPs from the Tanogris data set, and also for the contaminants, the sources that he and his team visual inspected were also publicly available. So we use that labels to train our machine learning model.
Have you made any pre-processing of the images?
Not directly, so we just use the raw cutouts and just only the converting from the normal counts to the surface brightness units. That was the only clip. And also we rescaled to so all the images depending on which survey will have different pixel scales, or sorry, pixel widths. So for instance, this was around 152 by 152 pixels. So we resized all these images to 64 by 64 pixels. So yeah, because machine learning models can only accept like this pixel bit. So if you have different surveys, different pixel scales will be there. So you will have different image cutouts and sizes. So to mitigate that, we resized everything into a common resolution.
And for the part of the prediction, have you made how you measure that prediction? Were also one part of the data set, or you took another way? For example, the identification of the artifacts.
So for
supervised, or you use another technique?
So for the identification of artifacts as well, so we had the labels from Tanogris. So we set everything as 0 and all the LSPs as 1. And when the model predicts everything above 0.5, we treat it as an LSB candidate. And then we also do the statistic profile fitting and also do a visual inspection to confirm these galaxies are actually LSB. So So I don't have the probability distribution now, but when we had the probability distribution from the model, it was kind of binary peak. So all the majority of the sources were peaked at 0 and majority of sources were peaked at 1. So the model was very clearly distribution between what is a 0 and what is a source that is labeled with 1 and what is a source that is labeled with 0. So yeah.
And those percentage of predictions, 90 something percent, were also part of the data set, a test sub data set.
Sorry.
For making the predictions, you show some percentage of accuracy.
Yes.
That was also part of the data set, or was
no, it was like a completely. I mean, it was part of the whole data set, but during training, we split the data into 80% is for training, 10% is for validation, and 10% is for testing. So this when we so this data set that we used for testing was not part of the training, so it was kept as a separate data set.
How bright how faint are these sources in surface brightness, more or less?
So in DAS we were using the definition that all the sources fainter than 24.2 in the G band are considered as LSBs.
So what is the main observational challenge to increase the samples of these objects? Is it the noise characteristics of the detectors, or is the observational techniques to get the data? What do you think is?
So it will depend on who we are asking. For instance, one of the main problem is the sky background subtraction. For instance, when Euclid was doing the standard, when they were looking at the Euclid standard pipeline, they found out that the LSP features are not kind of conserved and they are kind of over subtracted. And also, so this is the HSC data set, and here you can see that towards very bright, if there is a very bright source nearby, then you tend to over subtract the region, and it can cause, if there is an LSP nearby, for instance this is a cluster, so probably it will have a lot of satellite dwarf galaxies that are in the LSP region. So probably you're kind of destroying the whole structure of those kind of galaxies. So if you don't have those galaxies in the data set itself, you will not be able to find them with any kind of machine learning models or anything. And that's one major problem. And the second problem or the second difficulty is the noise and instrumental artifacts. So when you go from one survey to another, what is kind of an artifact in the physical sense will be understood by the model, because the model sees a lot of kind of physical artifacts, but the instrumental artifacts is kind of very designed for that instrument. So if one instrument will have different kind of artifact, whereas the other will have a very kind of different artifact. For instance, Euclid had very optical ghost where it was looking like a very round kind of sources. It was something, I don't know what it was exactly, but those sources were looking like a very good LSB or UDG, but it was actually an optical ghost. So this kind of instrumental artifact can also cause a problem.
So you need to have a very good knowledge of the BSF, for example, of the system, no, in order to be able to.
Yeah, so the data itself is the main, like processing the data itself is the main big task. First, the sky background subtraction, and second, knowing what kind of instruments or instrumental artifacts or contaminants that would be there from the instrumentation or from the data pre-processing.
Thank you for the talk. It was very nice. So you mentioned how the challenges in identifying these galaxies relate to having a lot of redshift measurements, sources being very faint, and so we cannot look extremely deep. But you also said that there's, of course, this is the typical question of the new telescopes, new data sets, and there's a cosmological tension, right, between the predictions of how many of these galaxies we can observe and the actual amount that we observe. So do you think with Euclid and new generation telescopes we might be able to solve some of these tensions? Do you think this is like intrinsically wrong with the model, or like does the new redshift and maybe new depth improve? Maybe we're looking at some bias in like looking at only local universe.
So ideally, if we have the redshift for all these sources, then we can say a lot about the cosmological tensions as well as for the problems with the galaxy evolution and like these kind of problems that we might encounter. But usually the major problem is not the identification or the initial identification of the LSBs, it's the lack of redshift. And since majority, and also these galaxies are very faint, so we cannot see a lot of LSBs or dwarfs in the higher universe as well. For instance, for all the samples that we have identified, the redshift distribution stops at it's only up to 0.1 or 0.2 max. After that, we cannot see much of the sources, because we, even with LSST and Euclid, we can cover some part of these LSBs and UDGs, but not. I don't expect a lot of sources to be detected beyond 0.5. It's just that these galaxies are very, with JWST or HST, you can find these kind of sources, but with their field of view is very small, so we will not be able to do much statistical studies with that. But it doesn't mean that we cannot do anything. For instance, I don't have the reference for now. So for instance, these galaxies have very shallow potential. So at least if you have like 100 sample of sources, then if you know what is the redshift and if you know what is the total number of global counts, then you can kind of estimate the dark matter profile. And with that, then you can try to identify if the galaxy, if the dark matter halo potential is cold or cusp. So those kind of problems can be resolved, even with some smaller subsample of the galaxies.
Do you have any idea up to what redshift we can expect a volume complete sample of these galaxies with these instruments?
So with LSST and Euclid, we can expect up to at least 0.3. At least this is just from my memory from seeing one of the presentations. So yeah.
Thanks.
Nice talk, thank you. I was wondering if, do you think that this approach and this method could be extended to LSB features instead of LSB galaxies?
Yes.
And to apply for the Euclid or.
Yeah, as long as you have, so the only problem is that this is a supervised machine learning approach. So as long as you have a label data set, you can use the similar. The main idea is that like instead of the model seeing the raw images, the model is also seeing the physical images. So that even if you go from one survey to the other, the model kind of still understand what is going on, like what is physical feature associated to that class.
And another question was more related with how do you determine the star formation rate of these galaxies?
So for this,
just with the colors or?
Not with the colors. So we used SED fitting. So for kids, we had 4 optical bands and 5 infrared bands. So we just use the 9-band photometry to estimate, and also the redshift. So we use the 9-band photometry to estimate the star formation rate and the stellar mass.
And are you able to determine also star formation rate gradients inside the galaxy? Or
we haven't tried that. So this is kind of new to us as well. So we just wanted to see how they will look like, and we stop after this point.
Yeah, because it could be really interesting to understand the
Yes.
origin of these galaxies.
Yeah.
More questions in the room? Enrique, can you check whether there is anyone in Zoom?
Are there any questions online?
Just unmute yourself and raise your, speak up.
Actually, I wrote.
Yes, one.
We can hear you, Alberto. Please speak up.
Okay, yeah, I was wondering because there are still uncertainties of the contribution of pale galaxies to the optical cosmic background. I was wondering, have you guys tried to estimate this contribution from your sample to the total optical background? Because that would be really interesting, or if you guys have planned to do it.
So we haven't tried actually, and also we haven't thought about that, to be honest. But it's thanks for the nice suggestion. We will try to think about it. How to proceed.
Okay, thanks.
Anyone else from the world?
No.
So I have a couple of questions. I know it's kind of late, but one of them is you were showing the behavior with the distance from the center of the cluster, and you were looking at the colors. Have you look at for a given mass, what is the surface brightness, the average surface brightness? I mean, in order to see if they're actually puffing up when they enter the cluster. So do you see have a gradient there or something like that?
We haven't tried that. We try to see how they look like in the size mass relation to see if we can distinguish between dwarfs and UDGs and the normal galaxies. And what we found out that LSBs and UDGs are kind of like an extended population of the dwarf galaxies. But we haven't tried to see how it will look like for cluster and field to see.
Or as a function of the distance to the cluster. No, because I think the color is the same thing that is happening in the more massive cluster. So it's just. But if you look at the structural properties, then you can know whether there is intrinsic properties based on the cluster, or they are just morphologically evolving, which is another possibility. Another thing that I had is it's nice to try to reproduce the human brain, which is what is happening here. But it's true, and you said that one of the problems that you switch from one survey to the other, and that of course you have to retrain. Is there any way, because I don't have any idea about machine learning, so yes. Is there any way to do kind of a hierarchical training in a way that the machine will know that it's in a different cluster? Because when I look at an image of a Galaxy or HST or Euclid, I know that what I'm dealing with because I know that, okay, this is a space telescope, I expect this has a PSF with 4 spikes because it has the secondary has this structure. So is there a way to train this so it's ready to be aware that there is a change in the cluster, meaning the survey,
So there is the other kind of models known as foundation models. So the ChatGPT that we use is kind of like a foundation model. So it's not designed for one specific task. It has been trained on like all the data that they can get. For instance, in astronomy, we have some foundation models. For instance, one is called SUBO. SUBO has been trained on all the galaxy images that have been available in the SU universe. It's like a citizen science platform, and people have been asked to classify morphology. So they have like a lot of labels and a lot of images. Like I don't know how many, but like more than 1 million or 2 million. So they have trained the model on those kind of images. So like these images also needs to be retrained to actually give a very good performance. But these models are very good. The good thing is that we don't need very large number of labels. Even if you have like 10 or 20, the model can, if you train the model with 10 maybe a bit less. But if you have like more than 100, for sure you can give very reasonable accuracies and performance. So there is a way with foundation models, but still you will need some like very fine retraining. But depends on the task as well. The task is like very simple, then probably you will not. But like for instance, if it's just the galaxy morphology classification, probably it will be able to identify the sources. But if you want to have like very good, like not just a spiral, elliptical, lenticular, those kind of, you have to have like the whole Hubble tuning diagram mapped out, then it's kind of tricky. So it will also depend on what kind of thing that you're kind of trying to do.
So eventually we'll be able to tell you, okay, this is an HST. And now I can tell you this is a spiral. Also.
And also there was one where they used ChatGPT and I guess it was Gemini. So they used ChatGPT and Gemini. They downloaded some part of the publicly available APIs, and then train the model with 100 examples of LSPs, and then they just give the images of the LSPs and write a prompt saying that this is galaxies are supposed to look like this, and this is how these features are. Then ChatGPT and these galaxies were able to classify them with 90% accuracy.
Okay. Any other question for Hareesh? No? Okay, so let's begin Yes, IPARCOS-UCM talk will be actually here this week. We'll have another LSB talk.